Lifting Mechanisms Part 2 of 2. Design on lifting mechanisms. The unit described a number of different lifting mechanisms, but which one will work best on a given robot? There are a few key considerations which designers should take into account when designing a lifting mechanism. Elevation required, object orientation, starting, configuring, and other size limitations, complexity, and motors required. Elevation required. The first and most important consideration a designer needs to take into account is the elevation required. At what height does the robot need to pick up the object? At what height does the robot need to lift the object? Are there multiple heights the object will need to be scored at? What mechanism will accomplish these changes in elevation? Object orientation. Another important consideration for a designer is the change in orientation the object will go through, if any. What orientation will the objects be when picked up? What orientation will the ball be when scored? Are these orientations different at different elevations? Starting configuration and other size limitations. VEX Robotics competition robots must start each match within a limited size, as described in the game rules released each year. This starting size may restrict which lifting mechanisms can be used. What if there is a bar on the field that a robot must drive under? Is this situation a designer may choose to design so his or her robot's lifting mechanism can fold down under the height of this bar? Some lifting mechanisms may take up more space than others. If the robot has a large hopper-style object manipulator, and it takes up almost all the space on the robot's starting configuration, the designer will need to find a lifting mechanism that will package into the space available. Some lifting mechanisms may fit better than others. Complexity. In some situations, multiple lifting mechanisms may all work. It is usually a good idea to choose the simplest mechanism possible which accomplishes the design goals. Motors required. Robots are limited in the number of motors and other actuators that they are allowed to use. A two-jointed arm requires two motors, one for each joint, whereas a single-jointed arm only requires one motor. Passive assistance. One expert trick used by many competition robotics teams is based on the concept of passive assistance. Passive assistance is when a designer adds something to the lifting mechanism to assist the actuator in lifting the load. Usually these take the form of counterbalances or springs. Using passive assistance can greatly reduce the load on the motors and allow for much faster mechanisms that lift much greater loads. The most common kinds of passive assistance used in the construction of VEX robots are elastic surgical tubing and rubber bands. These can be stretched in such a way that they contribute to the upward motion of a lifting mechanism. There are trade-offs involved in using passive assistance, but clever designers can use it to reduce the load of their motors and make their lifting mechanisms much quicker and more robust. In your engineering notebook, answer the following questions. Explain how the degrees of freedom will allow you to design a robot that is able to transfer motion as it manipulates game objects. Explain how a linkage system allows a robot to score on a high goal in a game situation. And explain how passive assistance can provide your robot with mechanical advantage.